students, today I am going to take the second rearrangement reaction called the Wagner-Meerwein rearrangement. You know, whenever you download a particular game from Play Store, you always start with the easy level first and then you move to the difficult levels. Same is the case with organic chemistry. What makes it beautiful is that you have the same set of rules and principles, but as you move to your higher classes, you apply those rules to the complex systems, something like this. So in today's video, we are going to do these kind of rearrangement. These are typical example of Wagner-Meerwein rearrangement, and we will also see how the mechanism is taking place. But don't get panic. Before we come to this, let's have some knowledge of the easy level. If I give you this particular molecule and I ask you to treat it with H2O in one case and ethoxide in another case, the expected product would be something like this. In the first case, you will say that the bromine will be replaced by OH to give you the substituted product. In second case, we will have an elimination product. The HBr will come out in this case and we will have a double bond between the two carbon, right? So these are expected products and no unexpected product would result here. But what if I give you a case something like this? In this case, this alkyl bromide when treated with NaOH gives you the normal or the expected product, but also a rearranged or an unexpected product. Here in this case you have OH at the usual place because the bromine will come out and OH will be there. So this is the normal product. But why the OH has come to this particular carbon? So you give the reason as that this alkyl bromide, when converted to its carbocation, this carbocation is the primary carbocation, and this primary carbocation rearranges itself to give the tertiary carbocation by doing the 1-2 shift or a 1-2 migration. The reason why this primary carbocation changes to tertiary carbocation is because tertiary is more stable than secondary is more stable than primary carbocation. So here what is happening? The 1-2 shift is occurring. One of the alkyl group from this particular carbon goes or migrate to this carbon, giving you a tertiary carbocation. And when this tertiary carbocation get treated with OH negative, will give you the rearranged or the unexpected product in a good yield, right? But this tertiary carbocation also undergoes elimination both in the Hofmann and Sedzeff rule and gives you the Hofmann product as well as the Sedzeff product. And you might have read the Sedzeff rule also, that particular product will be the major product which has the doubly bonded carbon more substituted. So here the doubly bonded carbon are more substituted, so this tertiary carbocation will give you this Sedzeff product in a good yield, right? So this is something that you have studied or done in your earlier classes. This is the easy level part. And before we move to the high level or the complex system, let's see some important points related to Wagner-Meerwein rearrangement. This is a 1-2 migration of a ring carbon atom in a bridged polycyclic molecule. I am going to tell you this in the examples that we are going to take. Bridged polycyclic molecules are complex systems. Whether it's a complex system or a simple molecule, there will be a 1-2 migration, right? So remember this. Also, a rearrangement will occur only if it leads to a stable carbocation, and that is the driving force, which is very obvious. Only when there will be stability there, whenever you are changing a primary carbocation to a tertiary carbocation, there will be a rearrangement, right? Also, if there is a relief in a strain, if there is a ring, and if there is a strain in the ring, and that strain in the ring can be relieved, then also the rearrangement will occur. I am going to give you the example for this case also. Such rearrangement occurs in the SN1, E1 or the electrophilic addition reactions of alkene. This is very obvious. SN1 is substitution nucleophilic unimolecular. In this case, the carbocation formation occurs. If the carbocation can rearranges to a more stable one, then that particular rearrangement will, obviously, it will occur, right? Okay. So, Now we can come to the complex system, because this is where the Wagner-Meerwein rearrangement is going to occur, or this is going to happen. So let us convert this camphinylol into a xanthine. Xanthine is a key component of fragrance of a sandalwood oil. So you can see this, in this case, the double bond has come here. So let us see how this particular reaction is taking place. So when the camphinylol is treated with H positive, you know what will happen. The lone pair from the oxygen will attack here, and we will have OH2 here. So the oxygen will get the positive charge. So obviously in the next step, the H2O will come out, and we will have a positive charge here. Now from here you can say that this particular hydrogen will come out, and we will have an elimination product. The double bond should come at this position, and this should be the product. However, this does not happen. The reason is that this particular is a secondary carbocation, right? I haven't shown the hydrogen here. So secondary carbocation rearranges itself to give the tertiary carbocation, and that happens when one of the alkyl group, methyl group here, it migrates from this carbon to this carbon. If this is one carbon, then it migrates to the second carbon. So this is a 1-2 shift, or a Wagner-Meerwein rearrangement. So that is something very important. So it is from the secondary carbocation, it is changing to the tertiary carbocation, and it is giving rise to a more stable species. So now the elimination will occur, and we will have a product something like this. So the double bond was expected here, but it formed here because of the formation of a more stable tertiary carbocation, right? So that is why the camphinylol will convert to xanthine, right? Okay. Let us take another example. We will have isoborneol that we have to convert into camphene. If you see, this is a very tricky example of, and very earliest example of Wagner-Meerwein rearrangement. If you see the product, it is almost completely different from the reactant, right? So to do this particular case, I have colored the bonds to make the things a bit clear for you people. Now here you can see that if you look isoborneol carefully, you have this OH here. Now in the presence of H positive, the H2O will come out, right? From here the H2O will come out, and the positive charge or the carbocation will form in here. But the thing is, because there is a methyl group here, so we think that the methyl group should migrate here, but the incorrect alignment of the methyl group doesn't allow its migration, right? Instead, what happens, in my previous video, Pinacol-Pinacolone rearrangement also, I told you, whenever the migration will occur in such a way, if the two groups, if this particular bond and this particular bond, as you can see, this particular, if this is in the anti-periplanar alignment, remember, whenever there is an anti-periplanar alignment, the migration will occur. So instead of this methyl group, which has an incorrect alignment, this particular carbon has more tendency to get migrated here. So this bond will break instead of this, and we will have a completely different case. So here, this particular bond is getting migrated to this carbon, and look it carefully. The Wagner-Meerwein rearrangement taking place something like this. So this green bond, it has broken from the carbon number 3, and this bond gets attached to this particular carbon, right? So that the positive charge comes to the carbon number 3. The reason behind this is that this one is a secondary carbocation, you can see, and here when the positive charge comes to the carbon number 3, this is a tertiary carbocation, right? Now this one is a little complex for you. So look at this. If I hold this particular carbon and I try to stretch it out, outside, this will be something like this. It will result into something like this. This is something like an open book, right? And now if I give it a clockwise direction movement, it will form into this. Fine. This blue bond will come in the upward direction and we will have a compound something like this. Now here the carbon at the third position, one of the hydrogen which is attached to the carbon, this will form the bond here and the elimination will occur to finally give the camphene. So we were expecting that this methyl should get migrated here, but instead this methyl is not getting migrated, rather this green bond or this particular carbon is getting migrated because of the anti-periplanar alignment, which is a favorable condition for migration to occur, and that is why we have a rearrangement something like this. This is something very important, a very typical example of Wagner-Meerwein rearrangement, right? So this is important. And the third case that I take is that of alpha-pinene converting into bornyl chloride. So here we are not talking about the carbocation stability. Here we will talk about how the strain in the ring is being relieved. So this is alpha-pinene and this is a 4-membered ring in this. So what happens is that in the presence of H positive, when the positive charge, because this hydrogen gets attached here, so we have a positive charge here, as you can see. The positive charge has come to this carbon because this is a tertiary carbon cation, more stable. If the hydrogen has come here and the positive charge would have come here, that would lead to a unstable one, because then it would be secondary carbocation, which is less stable. So that is why the hydrogen has attached here and we have the positive charge at this carbon. Okay. Now, this particular case is the one where what is happening is that because this 4-membered ring is highly strained, this is unstable. So in the presence of a positively charged carbon or a carbocation which is nearby, this will try to open up. So when it will try to open up, it will do the Wagner-Meerwein rearrangement, and as you can see, this bond has opened up to give this particular rearranged product. So here now we have a 1, 2, 3, 4, 5-membered ring which is less strained, and the positive charge has shifted to this carbon. So in the presence of a nucleophile or a Cl negative, now the chlorine will attach here and we will have a product something like this. This will rearrange to give us the bornyl chloride. This particular hexagon ring is this particular hexagon ring, and this part is this part. So that is how it has been formed. So that is how the alpha-pinene has converted itself to bornyl chloride. The Wagner-Meerwein rearrangement has taken place. So till now I think most of the thing related to Wagner-Meerwein rearrangement, how the rearrangement is taking place and how the mechanism is taking place, this is clear to you. If there is any doubt in your mind, please put it in the comment box. We will meet in the next class, next video, and if you like it, please subscribe the channel. All the very best. Thank you.